Some people said they would go and have a nap. I didn't get to have a nap. I had to work in the meantime, but that's okay. So we did sort of the basics of convection this morning. And we got to the point where we want to look at what does convection actually do to the atmosphere at the scales that we are interested in. I've had a few questions what we mean by large scale. So think a few hundred kilometers, okay? It's not very well defined. In models, when we do this averaging that we did on the board, in models, usually the average means the average over one grid box. And then the prime things are the variations within that grid box that we are not resolved. And then we say, okay, so the average values are what our model equations we can calculate using numerical methods, and then what needs to be parameterized are all the processes in between. When we use observations, and I'll show you observations of this on the next slide, then often the areas are even a little bit bigger, sort of 500 kilometers maybe, order of. It depends on the experiment where people put the radiosonde arrays out. Okay, so we saw that convection, or that, the other question I had, so is it convection or is it other processes? And of course, the equations don't know what the condensation is, what the evaporation is, and what the subgrid scale vertical transports are. So it's really for us in our mind, we say, okay, for the purpose of these lectures, since we're thinking about convection, we will be assuming that most of the condensation, most of the evaporation, and most of the vertical transport by these subgrid scale fluxes is done by convection. In reality, nearer the surface, most of the fluxes are turbulent fluxes, but they can be buoyancy driven as well. So they can be buoyancy or shear driven, but most of them are buoyancy driven. So in our definition of what is convection, that's convection too, right? Dry mixed layers are still convective boundary layers because the main force involved is buoyancy. But we know that condensation and evaporation happen also outside of convective clouds, right? They also happen in fronts, warm fronts, and things like that. But for the purpose of this exercise of the next few lectures, let's just assume that we are in an atmosphere that has a lot of convection in it, a lot of deep convective clouds. And then it's fair to say that the largest contribution of all this comes from the convection. As I said, the left-hand side here, these so-called large-scale terms, we can actually measure, and that we can measure them by putting an array of radiosondes out, measuring the mean of moisture, temperature, and hence dry static energy, measuring the mean winds. And to get the vertical motion, we actually need to measure the divergence of the wind, which means we need to measure the wind along some sort of line integral, which we can then convert to calculate convergence and divergence into the region. Okay? And then if we have all these terms here for measurements, then we know what the right-hand side must be, right? So we know what the effect of convection must have been if we have measurements of all this. So I'm going to show you some results. In the radiation, we often can calculate using a radiative transfer model, given the profiles that we've measured. So I show you some results. So the top one is one of the oldest experiments where people have tried to measure this left-hand side and then deduce the right-hand side based on those measurements. That what's plotted here, as you can see, it's actually not the Q1, but it's the Q1 divided by Cp, so that it becomes a temperature, basically. So it's the heating rate from convection, Q1, and you can see the profile. This is from an experiment in the Marshall Islands. The Q2 is this a conversion of the, again, it's the Q2 divided by Cp, really, to make it into equivalent to this Q1 calculation. And then here on the left, you see the estimate of what the radiative cooling of the atmosphere was. So the atmosphere, in most regions, cools radiatively, right? And then the convection heats the atmosphere. So that's the first thing we see. Convection heats the atmosphere. The left-hand, the vertical axis is pressure. So we see in this particular experiment, the peak of the heating is at about 500 hectopascal. So the strongest heating effect of the convection in this particular experiment is in the middle troposphere. And we see that the moisture effect is the same. The atmosphere is actually drying. Okay, so convection dries the atmosphere. The physics, if you can't think of it in any other way, is it just rains, right? And so the moisture that makes the rain has been taken out of the atmosphere. So there's a net drying effect from convection. The peak of that drying in this experiment and in most others is actually below the peak of the heating. That has simply to do with the fact that Q reduces with height so strongly, right? So the effects will get less and less because there's less and less water left in the updraft parcels. This is another experiment where people put out radiosondes. This was in the tropical East Atlantic during the GATE experiment, and you can see very similar results. The convector, the Q1 is the solid line here, heating of about 4 or 5 degrees a day. This one was 5 to 6 degrees a day. Drying of the atmosphere equivalent to also 5, 6 degrees. Again, the peak of the drying is below the peak of the heating, and the radiation is just a sort of profile of cooling. You can see this is just an estimate because it's not very structured. Then someone went and actually collated all the different field experiments. And you can see there is quite some variability in this Q1 term. The mean is this black line. But one of the things that you can already see here, and we'll come back to in a minute, is actually the peak of the heating. If you average over each of these colorful lines is one of the Q1 estimates. You see one odd one out here where it's actually negative, and that is from a shallow convective experiments. I should come to that in a second. But so this is all from deep convection, or precipitating deep convection, which is where the heating comes from, effectively comes from the condensation in the updrafts, right? But you see the peak is actually a bit higher if you average over all these different experiments. It's more like at 400 hectopascal rather than in those two, where, well, this has a hint that it's quite high, but this one, the peak is between 500 and 600 hectopascal. So this was a bit of an unusual experiment compared to many. Here's a list of all the experiments they included, but there's a sort of high-level peak in the heating. Now, shallow cumulus clouds don't really produce much rain, so their net effect is actually quite different from deep convective clouds, and it's shown here. You can see this is from a shallow cumulus experiment where the clouds were only, up to about 3 kilometers deep. And what we see is that in the lower, if you look at the Q1, this is the solid line again, in the lower part of the atmosphere there's a heating, or not, very low down there's a heating, and higher up there's a cooling. And the reason is that there's net condensation in the lower part of the cloud and net evaporation in the upper part of the cloud, because the material, so we get an updraft, there's condensation initially, and near the top all the condensate gets put out into a relatively dry layer, and it evaporates. And so in the upper part of a shallow convective cloud layer, the evaporation wins over the condensation, and in the lower part, the condensation wins over the evaporation. So the effect on the heating is therefore you get a warming low down and a cooling higher up. And in the moisture tendencies, you get a strong moistening, right? Q2 negative means moistening by the way it's defined. And that's because all that water, all these little droplets from the shallow convective clouds are being detrained, put into the environment, and they evaporate then. So you get very strong moistening in the upper part. But you see this is all in the lowest 300 hectopascal or so of the atmosphere. So this is all stops at about 700, right, hectopascal, so compared to deep convection. Okay, one important thing about deep convection is that it's not just the little convective drafts, but often convection is organized and has a large anvil cloud associated with it. Even if it's not organized, there's often, even individual cumulonimbus clouds have large anvil clouds associated with them. So there's not just rainfall in the part where we have the buoyant forces doing most of the work, but actually there is also usually a large area of stratiform precipitation associated with convection. Okay, so that makes sense. And that changes the way the heating profile structure in the vertical works out. And this is illustrated in those two diagrams here. So the conceptual picture that we have in mind, there's a convective updraft here, and that's usually very small. And when the convection gets organized, it could be a squall line, but that squall line has scales of a few kilometers to a few tens of kilometers, right? So that's that part here in the schematic. And in that part, the air is going up very rapidly, driven by the buoyancy force, mostly. That's the convective part. In the stratiform part, that we get actually upward motion above the melting level, 5 kilometers till the top of the cloud, which is where the convective cloud tops are as well, at about 10, 12 kilometers, say. And below that, we have precipitation falling out of those clouds into dry air and evaporating. So you can imagine that, so what that means is that, well, let's look at the bottom one. If we have no stratiform rain, then the heating is really concentrated in the middle troposphere. So the convective part of the cloud system makes heating in the middle troposphere at about 5 kilometers. That's where the peak is. And that has to do with the strong condensation in the convection together with the vertical motion that's taking place. We'll come back to that tomorrow a little bit more. In the stratiform part, on the other hand, the heating, the condensation only happens in the upper half of the cloud. In the lower half, there's actually evaporation from the rainfall that comes out. So really, there's a cooling, and this is depicted in this picture here. So the convective, the total heating this is from a paper by Yanai and Johnson, so I think it's based on this Togakor case. So again, it's one of the field experiments. The total heating is the solid line. The convective heating with or without radiative effects is this dashed line, and you can see it really peaks at 4 or 5 kilometers. And then the heating part from the stratiform part is positive in the upper troposphere and negative in the lower troposphere. So if you add this one and that one together, you get this total one. If you're a little more, this is more idealized here. If there's no stratiform rain, your profile looks like this. The more stratiform rain you add to your convection, i.e. the bigger the envelopes, the more organized the convection is, the more this net profile shifts to higher levels. So you can see one thing that happens from adding this shape profile to this shape profile, or in this case this bow shape profile, is that the peak of the heating moves up, right? Because of this extra heating higher up from the stratiform clouds. And below, the heating actually gets reduced. So if you assume 40% of the rainfall is stratiform, then you can see you get this reduced heating lower down and this increased heating higher up. So you really get that. And if you make it 70%, then you even get net cooling low down and very strong heating high up, and the peak shifts higher up. Now it turns out this is very important because if you do calculations how waves in the tropics respond to convective heating, where the peak is matters a lot to their response. Okay, so things like the MJO, for instance, very much rely on this top high level, the peak being higher up in the atmosphere. And one of the reasons we think GCMs cannot make the MJO very well and cannot maintain it very well is that their heating peak is too low, right? They don't represent these stratiform processes very well, and so therefore the heating profile that parameterizations and current climate models produce is much more like this convective one. There's no stratiform precipitation, and the stratiform bit is kind of missing or weak in models, and therefore they don't connect to the waves properly. Yes?
What is the source for updraft motions above the 0 degree isothermic stratiform clouds?
Sorry?
What is the source for result for the updraft motion?
This one here. This, why is it going up here?
In the stratiform region.
Yeah, so once the stratiform, so what happens is once the stratiform region forms, you get this cooling because the rain falls out of it. You get cooling here. That induces a circulation into the cloud, which actually becomes an upward motion in response to the heating from condensation here. There's upward motion in the mesoscale, weak, but it's not nearly as strong as what happens in the convective clouds, right? So this is much less than, it's a few centimeters per second, but it happens over a very large area. So you get a circulation that's induced by the organization of the convection. And that circulation, that mesoscale circulation, leads to an extra condensation in this part, and there's even downward motion here. As a result of that cooling, the air starts to descend, again, not very strongly. So this upward motion, this mesoscale circulation, is what keeps the condensation going and makes the anodes survive for longer than they would otherwise survive, right? So that's all there is to it, really.
On what basis does a model decide steady form fraction?
Models, again, just like with the Cape closure, every model has a different way of deciding how much stratiform rain there is in a convective atmosphere. Some have prognostic cloud schemes where they move some of the water that was in the convection into the stratiform cloud. I don't think there's a single one. There was one parameterization, but I don't think it's used by anybody. I don't think there's a single one that makes this circulation. And the circulation is key to keep the anvil alive for a long period of time. Without the circulation, the anvil dies relatively quickly.
What about Mead's recent theory of slant-wise convection?
Yes, so there's theories around, but there's no model as far as I know. So the only person who had ever built a convection scheme trying to take this into account was Leo Donner, where they put some extra. I think in CAM, Brian Mapes and Rich Neal have experimented with it, but I don't think it's made it into any of the operational models. So it's still something. We can come back to this. I think it's one of the reasons why models, and we will come back to this on Wednesday when we talk about sort of what are the problems currently that need to be solved. And I think you will find this is one of them, that models do not really have a good way of doing that. Okay? So the reason, so you might say, why do we care about all this heating stuff? Who cares, right? But the reason we care about the heating from convection is that the circulation responds to it. And I just put this up as the simplest example is the Gill solution. If you put an idealized heating that looks like convection at the equator, you can see here's the heat source, then this is the response that is being induced. This is the vertical motion and the horizontal wind, right? So the vertical motion are the contours and the horizontal wind. So you get flow into the region of the heating. This is the sea level pressure anomaly, so you get two low pressure systems to the north and the south. This is if the heating is right at the equator, okay? And this is the stream function as a function of height, so you get this upward motion here, and then downward motion away from the heat source. So you get this overturning circulation. These are simplified solutions to the equations of motion with an idealized heat source at the equator, right? So the reason we care about this is that if we were to induce convection somewhere, convection happens somewhere, the circulation around that region will change. And this circulation often even reinforces the convection where it actually is happening, right? By providing extra moisture, by providing extra uplift, and so on and so forth. So that's why we care. All right, the next thing I want to talk about is equilibria. So there's several equilibria that we will look at. The most famous, perhaps, well, there's two very famous ones. One we'll start with is something that's called convective quasi-equilibrium. And it's being used as a concept for parameterization of convection in many models. Okay? It's just as an idea. And here's how people came up with this idea. This is from the GATE experiment, which happened in 1974 in the Atlantic. It's one of the most fascinating things if you think about the modern world versus the world in 1974. They had 12 ships participate in this experiment, and they were from all countries that you could possibly imagine. They all came together to do something together. So the Soviet Union was there, the Americans were there, India was probably there, Japan was there. All the ships came together from Europe, France, Germany. They all did an experiment together. Try this today. No chance. whatsoever, because everybody wants to do their own thing. And the reason these big field experiments don't happen anymore is because everybody wants to be in charge. I don't know how they solved this in 1974. If you go to anyone and say, I have this idea, I want to do this field experiment, they all say, yes, we participate, but only if we are in charge. And because not everybody can be in charge, they don't work together, right? Because if the Americans in charge, the Russians won't come. If the Japanese are in charge, the Koreans won't come. I don't know. It's always, if we are not in charge, we are not participating. So it's a very strange world we have developed into. But that's nothing to do with convection. So what they found in the convection, what they found in this experiment is they measured vertical motion. And this is a composite of the vertical motion. So this was in the Atlantic. So what they were interested in was there was these African easterly waves. They came over the Atlantic, and convection was associated with them. And they wanted to figure out how. So they made a composite wave, which is, you see here. R means ridge, northerly flow, trough, southerly flow, ridge. Okay, so that's the diagram. And they had several of them coming through, and they composited them all into this one diagram. So this is a composite of several of these waves coming across the array where they took the measurements. And this is the vertical motion. Okay, so you can see there's upward motion ahead and during the period where the trough is right over the surface pressure trough is over the chips, so over the array. And what you see is, and the units don't really matter, they are 10 to the 5 millibars per second, which is roughly millibars per day. But only roughly. You get this very strong ascending motion in the atmosphere around the trough. Now, if you calculated just from dry adiabatic processes how much that would cool the atmosphere, you would expect a very strong cooling of the atmosphere in the trough, right? Just because if you have this vertical motion, air goes up, it expands, it adiabatically cools. Very easy calculation. Well, so the expectation, if that was the only thing that was happening, is that you would have a very strong wave in temperature as well. Well, here's the temperature anomaly across the wave. So here's again ridge, it's the same x-axis as over here. And what you see is that essentially there was almost no temperature variation at all. These units are 0.2 Kelvin, so they have a warm bit. So it's actually warmest when the ascent is strongest, and only by 0.2 of a degree, which is nothing, really. It's very, very small compared to what was induced. So the conclusion they drew is there must be another process in the atmosphere that balances that cooling that comes from the ascent, and that process happens to be convection. And it happens so rapidly that actually you don't get any warming or cooling, even though you get very strong variations in the vertical motion. And that's where the idea of quasi-equilibrium was born. Basically, the idea is that as the large scale does something, the convection balances it almost immediately. They're almost in equilibrium, right? And another way to look at this is to go through the actual days in the experiment. So the x-axis here are days, and there are 3 graphs here. And really the ones that we're interested in is the middle and the bottom. So the bottom one is precipitation, right, averaged over the area. This one is the negative of omega, so where it's positive we have upward motion, right? This is at 700 hectopascal, and this is just the meridional wind. This is just to indicate where in the wave pattern we are, but it doesn't matter for our discussion. And what you see is when the vertical motion is very large, whenever we have upward excursions in this graph, we also have upward excursions in that graph. So the vertical motion and the precipitation are in some sort of quasi-equilibrium. Okay? So that's all there is to it. The idea of quasi-equilibrium is not very profound. It's actually very profound as an idea, but it's not very difficult to understand. The idea is the large scale has some vertical motion, it cools the atmosphere, and the convection compensates straight away. Okay, very simple idea. And temperature variations, therefore, in the tropical atmosphere are very small, despite the fact that there can be very large variations in the adiabatic forcing of that temperature. And it's because convection is a fast process that very quickly compensates for the cooling that would be associated with the motion. That's it. And we use this in models. And it's a nice idea for models because we have the separation of scales, which is very strict in our models, way stricter than it is in the real world. And so we get this large scale part. It does something, ends up cooling the atmosphere for whatever reason, and then the convection will make sure that there isn't a large temperature tendency. It will just compensate exactly for that cooling. So we can use that. If it was true, we can actually use it for modeling, right? We can say, how strong should our convection be? Well, it should be just about strong enough to compensate for whatever the large scale would do, the resolved equations would do if there was no convection, okay? Another equilibrium that one needs to consider, and it's very different, is the one that shallow convection is in. Okay, so shallow convection is often in an equilibrium. The trade wind regions are one of the most stable regions on Earth with very little variation. And here the balance is a different one. So in shallow convection, the layers that we are interested in is the subcloud layer, which we are also interested in deep convection. Then there's the cloud layer, and there's an inversion usually at the top. So here this is moist static energy, but you could plot potential temperature, liquid water potential temperature, virtual potential, any of your favorites. They would all qualitatively look the same. So what you see in the subcloud layer, this is mixing ratio, and this is moist static energy. This is virtual moist static energy. And what you see is really, if you just look at the most leftmost and the rightmost, in the subcloud layer, everything is well mixed, so these numbers are constant with height. Then the cloud layer, there's a small increase in this quantity, and then there's the inversion. So if you think of this as temperature, or theta V, there's a very strong temperature inversion at the top of the cloud layer. And this is maintained by subsidence, which is part of the Hadley circulation, of course, if you think the trade winds, right? So the balance between the terms is that you actually have subsidence. The subsidence above this inversion is completely balanced by radiative cooling. So if you think of an equilibrium, it means everything is steady. So the balance above the trade wind inversion is simply between subsidence and radiative cooling. Here, the balance is that there are surface fluxes that provide water vapor and heat to the atmosphere, which is then partially distributed into the cloud layer. The clouds grow into the inversion, and as they put water into the inversion, they cool the warmer part of the inversion, so the balance is very subtle here. The more energetic these clouds are, the more they penetrate the inversion, and the more, I go one back, if you put cooling into this warm part, then the inversion will get weaker, of course, right? And the cooling comes from the evaporation of water drops again. So there's drops in the clouds go up, push into the inversion, spew out their drops through detrainment, the drops evaporate, the inversion gets weaker. Well, if the inversion gets weaker, the next generation of clouds will go deeper, and the next generation will go deeper still. So in equilibrium, the equilibrium really between the subsiding motion and the clouds is entirely set. People have shown this, Björn Stevens has shown this in a very nice paper. It depends entirely on how much water is actually transported from the surface into this trade inversion layer where it evaporates. That sets the equilibrium height of the trade inversion layer. And of course that depends, so the question then is how energetic will the convection be? And that depends on the surface fluxes, which in themselves depend on the sea surface temperature very much, very strongly. So the warmer the SST, the more energetic the clouds are, which means this trade inversion is slanting. It's very shallow where the SST is cold, and it gets deeper and deeper as you go away from the cold SST towards the warmer SST, until you get to SSTs where you get deep convection and the circulation is different anyway. And then you're in the ITCZ. So here you have this increase in the height of the trade inversion. Okay.
So in the
What about the landmass? This is all about.
This is over the ocean. Yeah, I didn't really. Land is an interesting one. So over land, it's actually a good point. Most of my stuff is on convection over the ocean because that's the most studied. Because that's the one. over land, things change. So the one thing that changes over land is the sensible heat flux becomes more important. The Bowen ratio is changing. So the first thing that happens is the subcloud layer is deeper because the air tends to be drier, right? And also because much of the energy that the sun provides doesn't go into latent heat flux, doesn't go into evaporation like over the ocean, but most of it goes into heat, actual heat transport. That's during the day, right? And so you end up with deeper subcloud layers. You tend to get more, because the moisture isn't as readily available, the shallow convective clouds most of the time, especially if you go away from the coasts, are usually forced. They're very small. They're often like pancakes, so small in vertical extent, but a bit larger in horizontal extent. Whereas in the trade wind region, they're small in the horizontal and large in the vertical. So the aspect ratio of the cloud changes. For deep convection, the clouds tend to get a bit bigger. So they then can grow more easily because bigger clouds are less prone to entrainment. So lots of things happen over land. But I'm not going to talk about it much. Sorry.
So, see, like this deep convection, this shallow, I mean, models find it difficult in representing the low clouds as well, right?
Yes.
Marine static movements.
Yes.
And so, the point is that what is the key process, do you feel? Like deep convection in shallow, we don't have any trigger or closer, right? But it is driven by maybe top of the tubular strong.
So the key process in all of the shallow clouds is how much dry air, if you think this is the mixing ratio here, how much dry air is coming through this inversion. And in stratocumulus that's well studied as cloud top entrainment, but in shallow cumulus it's just as important but not as well studied. Because, why is it important? Because the only source of dry air that the boundary layer has is the free troposphere. Right? Because near the surface it's wet, because you're over the ocean. It's going to be wet. And if no dry air was coming in from the free troposphere, you get saturated very close to the surface and there's fog and so on and so on. Now but there's a very strong feedback. So if you have a strong wind, you get a surface flux. Okay? You have a steady wind over the surface, you get surface flux. The surface flux makes these clouds grow. You have strong surface fluxes, you get deeper clouds. Deeper clouds penetrate this inversion, they drag in more dry air, and that makes the surface flux even larger. So the key variable as to what sets the boundary. Why is this important? I should have put a picture here. Do I have it in any of the other lectures? It's important because if you think about the interaction of shallow and deep convection, for the circulation, for the general circulation, it's very important because where it rains in the ITCZ, it rains way more than what can evaporate from the surface. Okay? Does that make sense to everybody? So the rainfall rates in the ITCZ are up to 10 millimeters a day or something like that, right? On average over the year. But the evaporation is never more than 5. Actually, it's often less than 5 millimeters a day. So where do the other 5 millimeters come from? Where's the water coming from in equilibrium? And it comes in from the side. Okay, so if it comes in from the side, it means it comes in from the lower branch of the Hadley circulation towards the ITCZ. Okay, but how does it get into the atmosphere? It gets into the atmosphere through surface fluxes, right? Along the trade winds, along the wind that transports it in. Now, if these surface fluxes are large, there's more water coming in. If the surface fluxes are small, there's less water coming in. So from a modeling perspective, if you make this shallow convection too active, you will dry the atmosphere too much, your latent heat flux will be too large, and you'll be transporting too much water into the tropics. If vice versa, if you're shallow convection, people knew this in the 80s, when they didn't have shallow convection, the rainfall in the tropics wasn't strong enough in models in the 1980s. And what they found is it was because they didn't have shallow convection. They tried all sorts of things with their deep convection schemes and they couldn't solve it. And then they found, it's actually because we don't have shallow convection, so therefore there's not enough water vapor coming in because we're not ventilating the boundary layer. These days we have the opposite problem, and I often wonder whether the opposite problem that we rain too much in the tropics, most models rain too much in the tropics. And I wonder whether the reason isn't that we are doing too much with the shallow convection in the trade wind regions. But that's an aside. Yeah, so it's very important actually because the two play off each other. And I'll show you another context, another equilibrium that's very famous in which the two play off with each other, the deep and the shallow convection, okay? So this is from some recent work that we've done, and so I just want to show you this. So another very famous equilibrium that even has the word convection in the name is the so-called radiative convective equilibrium, okay? And this goes back to the 1960s, in fact, where people tried with very simple models to represent the lapse rate of the globally averaged atmosphere. Okay, so they wanted to know what sets the lapse rate of the temperature profile of the globally averaged atmosphere. And they did a very simple experiment with a globally averaged model. And so here's pressure, goes all the way into the stratosphere, as you can see, and here's the temperature, and this is global. And so the first thing you can ask, what if the atmosphere was in pure radiative equilibrium, no other process? What would the temperature profile look like to get to an equilibrium which only has radiation, nothing else? And you can see then you get this graph here. So you see the lapse rate is much steeper than what is observed. Okay? So then if you did a dry, then they say, well, what if there was mixing? And what if it was dry? There was no condensation involved. And then you get, basically you end up with the dry adiabatic lapse rate, right? That's the lapse rate you end up with. But then people that said that's also not what's observed. So there's actually, the dry assumption doesn't make sense. And so they said, what if we add convection to this? Just some adjustment that follows a moist adiabat, assuming that convection keeps the atmosphere close to moist adiabatic lapse rate. And then they got a lapse rate that looked most closely like the observed. So the conclusion is, in a global average sense, radiation and convection are in balance. So this leads to a very well-known fact that not a lot of people know, which doesn't make any sense at all. But what controls the global mean rainfall on Earth? What is it related to? Why is it what it is? What is the number one control on global mean rainfall on Earth?
Temperature.
Temperature, energy budget. Yes, they're all correct, but not quite. Sorry? Radiation has something to do with it, not just solar. We think of all these circulations and how the ITCZ and the fronts, and they all make the rainfall, but really it's entirely set by the global mean cooling of the radiative cooling of the atmosphere to first order. So if you think about it, if the temperature was to be constant and radiation cools the atmosphere, we need something that warms the atmosphere, right, to compensate for the cooling. And there's two things that can warm the atmosphere: condensation, right, and surface fluxes of heat from the surface into the atmosphere. So the fluxes of heat into the atmosphere are very small. The sensible heat flux averaged over the globe is very small. Few tens of watts per meter square, not even 20, somewhere near 10 on a global average. Okay, so that's not a lot. That's why I say to first order. The radiative cooling of the atmosphere is on the order of 100 watts per meter square, as I'll show you in a minute. So the other 90 must come from condensation. The water for that is provided by evaporation. And if we assume that to first order all the water that condenses falls out as rainfall, then the rain, which is not a bad assumption because the rainfall is 3 millimeters a day, what do you think is the cloud water content in the atmosphere globally averaged? Yeah, I tell you, it's about 0.1 to 0.2 millimeters a day, so much smaller. So the cloud water that's stored in clouds is very, very small compared to the water that falls out, right? So to first order, we can say everything that condenses falls out. So that means the radiative cooling of the atmosphere and the rainfall must balance to first order. There's a small terms like sensible heat flux and storage in clouds, but they are very, very small. So to first order, that's the balance, right? So you can turn this around and say, so if we change if we want to change the global mean precipitation, we need to change the radiative cooling of the atmosphere. Okay, and that's what's called radiative convective equilibrium. So on the next graph, you can I show you something that's really interesting. We've taken some data. This is from 2 years of data. We've since done it for about 10 years of data. We now have satellite observations that are good enough to make it possible to estimate what the cooling of the atmosphere is, radiative cooling of the atmosphere is. And already, I told you already, in the global mean, this matches precipitations, and that's the assumption of radiative convective equilibrium. Right? Most of that condensation is done by convective motions, not by non-convective. So here's a map of the atmospheric cooling. And you can see it's actually the maximum cooling is blue and the minimum cooling is red. And the maximum cooling happens in the trade wind regions. These are regions where there's emissions from very low down, and above those very moist and often cloudy layers, there's a very dry atmosphere. So the atmosphere is very efficient. So the solar part is a small warming, and the long wave part is the cooling part here. So really the cooling comes from the long wave part. The solar part is, if anything, it's a small warming because there's some absorption of solar radiation in the atmosphere. But it's small. As we know, most of the solar radiation goes in and out, and that's it. And it's absorbed at the surface, but it's not absorbed in the atmosphere much. This is the atmospheric budget, right? It's not the top of the atmosphere, it's not the surface, it's the difference between the two is what drives the atmospheric budget. And this is precipitation. So the first thing you see is whilst on global average, the cooling, the more it cools, the more it rains. Locally, this is not true at all. You can see where the precipitation is strong in the ITCZ, the cooling is the weakest. So we immediately learn this radiative convective equilibrium, while it's true in a global mean sense, is probably not true locally. So this doesn't work locally. So that's quite important actually, which is why I put it in here. Because there's this misconception that this radiative convective equilibrium concept is a good concept locally. Well, I'm telling you here now it's not. So you can go further, and you can make scatter plots. This is what we have done here. If you go in the West Pacific, and you take an average, and this is a single grid point in the West Pacific. The x-axis is the radiative cooling, right, atmospheric, and the y-axis is in precipitation. And we've converted the precipitation to energy, watts per meter square. You just multiply with L, and you get this. So 1 millimeter of rainfall is roughly 30 watts per meter square. And what you can see is this is not at all radiative convective equilibrium at one grid point. It's the opposite. The more it rains, the less it cools. And the reason this happens is that you make clouds. Associated with the rain is deep convection. Associated with deep convection is a lot of high cloud, annual cloud, cirrus cloud, and they block long wave radiation. They have a strong greenhouse effect. So the cooling of the atmosphere gets reduced because the emission to space comes now from higher up in the atmosphere because of the clouds. That means it's lower because it goes with sigma temperature to the fourth, right? And you really need to average to about almost globally to get some sort of thing that looks like equilibrium. I'll skip over some of this because I will present it on Thursday in the lecture to the Royal Meteorological Society, and we have to move on a bit with time. I wanted to do one thing at the end, is I want to stress this importance of organized convection. So we've already seen that the organized convection is important because its heating profile looks different from disorganized convection. So remember, disorganized convection, the heating peaks in the middle troposphere, 5 kilometers. For organized convection, because of the presence of these big anvil clouds associated with it, it peaks higher up in the atmosphere, more like at 6, 7, 8 kilometers is where the peak is. That's important for how the convection then interacts with the waves. That's why we care. It's really the bottom line. All right. So where do we find organized convection then?
I have one small question.
Yes?
How do we define a convection as an organized convection?
Yes, so that's a good point. So there's different ways people define it. The most common way is actually this one. The most common way is to say how much of the rain in a relative sense, comes from stratiform rain versus convective rain. Okay, so that's one way you can define it. Another way to define it is to find structure, of course, wall lines, big angles, but that's very difficult to do in a sort of global sense from global data sets. You can do that for your favorite radar site, and you can find all the score lines and stuff. So the most common definition is by what is the relative importance of stratiform rain in the total rain. And a good sort of rule of thumb is if more than 50% of your rain come from stratiform rain, 50% or more, 40% or more, then the convection there must be some mesoscale circulation, because otherwise you couldn't get that much rain from stratiform, and so therefore the convection must be organized. So that's one. Another one we use is, I might have to go back here after all. Another one you can use is you can look at the cloud signature and say how much of the area is covered by thick anvil clouds. And the way we do that is we use some information from a data set called ISCCP. Who has heard of ISCCP? Not many. ISCIP, also known as ISCIP, right? So ISCIP is a data set that measures clouds, and the reason it's become famous is because it's the only data set where you can make a climatology for very long periods of time, because they use operational satellites to do it. They use geostationary satellites and also polar orbiting satellites, but they use very simple measures only, which is what they get criticized for, that it's actually very simple compared to modern satellite technology. So they use only information from very few channels. But because they use only information from very few channels, they can do it across the world with all the satellites there are, because they all have those channels, and they can do it for the long period of time. And they started in 1983. So what you do is for every pixel, so you can make a grid box, and ISCIP usually makes 2.5 by 2.5 degree grid boxes. The latest release only makes 1 by 1 degree grid boxes, but this is all based on the 2.5 by 2.5. And then you look at all the pixels in that grid box, and you determine where's the top of the cloud, and you determine that from the IR temperature that you can measure in the infrared channel, and you ask what is the optical thickness of the cloud, and for that you need a visible channel, so that's only available during daytime. And then what you can do is you can count how many pixels of a certain optical thickness cloud to pressure combination did you find in your grid box, and you make a histogram. But it's a two-dimensional histogram, right? Because there's two variables involved: cloud to pressure and cloud optical thickness. So that's what these guys are. On the x-axis is the cloud optical thickness. From left is low, right is high. On the y-axis we have cloud to pressure, where low pressure, high tops is up here, obviously, and high pressure, i.e. low tops, is down there. And then all we did is we apply a cluster analysis, and I won't go into the details to this. And what we find is that there's actually one cloud regime that has a very high occurrence. So red means many pixels, yellow means not many pixels. And you see you get lots of pixels of high clouds that are very thick in one particular regime. All the other regimes, if they have high clouds, they are thin. Okay? So it turns out, and I'll show you this in a second, is that this cloud regime also represents organized convection. Yeah, does that make sense? So there's another way of defining organized convection is by looking at the clouds that the convection makes. So one is you look at the rain that the convection makes. If a lot of that rain is stratiform, it's organized. The other one, you look at the clouds that the convection makes. If a lot of the area is covered in very thick clouds, then it's also organized. Okay? So those are the two most common ones that we use. So here is the first one, the rainfall. This is a map, and this is made from TRIM. Quite a while ago, the paper came out in 2003. So there's a lot more data to do this now, but in those days, there wasn't all that much data. But that's basically a count over the Earth of how many pixels do you, in TRIM, were stratiform, how many pixels were convective, and how many pixels were shallow, isolated pixels. Okay? And the definition is made based on the radar information from TRIM. So you look at the maximum in reflectivity? Is it just a single blob? And how deep does that reflectivity go in the atmosphere? If it's a single blob which goes deep, then it's convection. If it's a single blob that goes shallow, then it's the shallow isolated. And if it's widespread rather than a single blob and probably not as strong, then it's stratiform. The most important thing to note is they look almost the same, but this is 10 to the 4 and this is 10 to the 3. Okay, so there's many more stratiform pixels. But this just shows you where they are. And so where there are the most stratiform pixels, that's where we think there's the most occurrence of organized convection. And you can see it's where the SST is warm, as well as over the islands of the maritime continent. It's in the East Pacific, and also over the land regions there's a fair amount. Once you get to these 30 degrees, it's mostly not convection anymore, but actually fronts that penetrate into this region. Okay? Whereas the shallow isolated stuff is mostly in the trade wind regions. If you do it by cloud regime, so as I said, if you use these cloud regimes, i.e. the cloud signature of the convection, you find that most of the organized convection happens in the ITZZ region, whereas most of the non-organized convection, and there are two types, deep non-organized convection and not so deep non-organized convection. So let's just call it not so deep, right? And you can see the organized convection is mostly in the ITZZ, the non-organized is more widespread. And then the same regions that have organized convection also have this not so deep congestus type non-organized convection. These numbers here are the frequency of occurrence. So you see the organized convection is actually quite rare. Happens only a few % of the time in space on Earth. So it's not a very frequent occurrence. This is very important because of the next figure that I'm going to show you. So keep in mind, say 5, 6, 7%. Same for the not so organized deep convection. The shallower types are present about 25% of the time in a tropical average. This is averaged over the whole tropics. Now comes the kicker.
This is from which?
This is from ISCCP.
Oh.
This is from ISCCP. The bit that you missed because you had to step out.
Yeah.
But this is the key thing here. This is the contribution to precipitation. So this is the organized convection, this is the not organized convection, this is all three together. What you can see this and this is the PDF of rainfall when we are in this organized convective regime and when we are in the not so organized convective regime. And you can see a massive difference between them. So and this is area averaged rainfall, right? It's averaged over the 2.5 degree grid box of ISCCP. All right, we use GPCP data to do this. And what you can see is the organized convection rains twice or more when it's present than any other convection in an area average sense. All right, so it's very important in that it rains a lot in organized convection. In fact, that's the number at the top. 47% of the tropical rainfall comes from organized convection. So almost half the rain comes from this type of convection, and it occurs only 6 or 7% of the time. All right? So it's, relatively speaking, making a lot more rain than any other convection does. So disorganized convection doesn't make that much rain, and it doesn't because in an area average sense, it's not that important because locally it rains a lot, where the convection is. But it isn't in many places in a grid box of 2.5 kilometers. So to make a lot of rain in a grid box, you actually need this stratiform part. And this comes back to the GCMs, right? GCMs, if you don't have that stratiform part well represented, and you still want to make a lot of rainfall, you need to do way more convection than you should. And I think that's the problem with current models. They need to make way more convection in their grid box because they don't have the stratiform part. To make the high rainfall rates, you therefore have to overcook the convection scheme. Otherwise, your model misses all the high rainfall rates.
Overprediction. Some models are giving overprediction.
At the very high end, they give overprediction, but not in the middle. They don't actually.
So from the radiative, budget balance perspective.
Yes.
So which one is more crucial? Is it that which are persisting less but producing more rainfall, or like shallow clouds persisting more but draining less, or both?
From the radiative balance, actually, it turns out that the OLR differences between organized and not organized convection are not nearly as big as the... So if you think about top of the atmosphere radiation, there is a difference in OLR between organized and not organized, but it's much smaller than the difference in rainfall. So the organized convection, because it has non-organized convection, still makes large amounts of cirrus cloud, but they are thin. They don't produce much precipitation, but they are thick enough to be changing the radiation balance. So for the radiation balance, it's these thin clouds that we worry about. For the precipitation, it's the thick ones that we worry about. So it's different types. Okay, the shallow clouds are important because they act on the solar radiation a lot, not so much on the long-wave radiation. Okay, the only thing you need to take away from this one is that this organized convection stuff is actually quite important and it makes a lot of rain. And the final figure of the day is from a paper a student of mine did, looking at trends in rainfall and asking the question, is the trend in rainfall somehow related to this organized convection or not? And what he found was quite surprising. So this is the trend in rainfall, and it's short because we don't have all that much data. So trend is not quite the right word. But this is the rainfall trend from 98 to 2009. We've since done it to 2015 and results haven't changed. And you can see that there's this wetter regions in the, and it almost doesn't matter whether it's trend or variability. Don't think climate change here, right? I'm not trying to convince you that this is climate change. I'm just asking, as the rainfall varies, what role does organized convection play in that variation over several years? Okay. And so this is there's an increase here, there's a decrease there. This is the same map, but this time we just show you the frequency of occurrence of organized convection. All right, and so you can see that where the rainfall has increased, the frequency of organized convection has also increased. Okay, and where it has decreased, the frequency of organized convection has also decreased. So there's a relationship between the two. This is not just the frequency itself, this is the contribution of the change in frequency to the change in rainfall. So it's already, the units are the same as here. So the blues mean exactly the same. This is the contribution to the overall change in rainfall of changes in intensity of the rain. So when the organized convection is there, how much does it rain? And as you can see, if anything, that has been reducing, not increasing. Now that's a bit of a surprise. That was a big surprise to us, because everybody's talking about this very simple, rainfall has to go up because there's more water vapor in the atmosphere, so when it rains harder. That's not at all what we see in the observations. What we see is that the frequency, so yes, there's more water vapor in the atmosphere, but it doesn't lead to more intense convection, it leads to more frequent convection. Okay? And this is what the other types of convection do. So this was the organized convection only, and this is if you take all the other types of convection. You can see, yes, they also contribute a little bit to the trend, but the overwhelming contribution, once again, comes from organized convection. So again, organized convection is not just important in that it produces a lot of rain, it's also important in that the changes in the rainfall seem to be mostly associated with changes in organized convection, which again throws a challenge at climate models. Because if most of the action in variability and change is in organized convection, then one of the priorities that we have in climate models is to represent organized convection really well. And we really don't represent it very well at all. We represent the disorganized convection, but the organized convection, as you will see tomorrow when we talk about convection parameterization, we give almost no thought to this stratiform bit. It's all about the updrafts and entrainment and all that. We'll talk about all that tomorrow. But very little thought goes into, if any, goes into what happens to the stratiform part. So that's a problem. And I think we'll leave it there. Thank you very much. And I'll see you all bright and early, not so early. 11?
11.
11?
I think so.
11 o'clock tomorrow. I'm not in charge, I'm just giving the lectures. Partha is in charge. So if he says 11, then it's 11.
I think let's take that.
Alright, we'll see you at 11.
Any questions if you
We'll
want?
see you at 11. So yeah, let's have a quick discussion.
Yeah, 11.
Yeah.
How does the large scale atmosphere determines when and where to influence the small scale convection?
How does a large scale atmosphere decide whether...
Determine when and where to influence the local scale convection.
So this is an interesting one. I have a figure on this at some stage in the lectures. So there's an interesting question is it, so there's several schools of thought, okay? One school of thought is the thermodynamic school of thought, which says the convection drives the circulation. So the convection happens spontaneously, there's warm surface either over land or warm SST. Convection develops, and then the circulation responds to that, and then the convection gets amplified, if you want to think of it that way, by the circulation. There's another school of thought that says there's circulations in the atmosphere always, and the circulation, where that circulation has upward motion associated with it and convergence and so on and so forth, that's where the convection will occur. And I think the truth is in the middle. You get both types of convection. Because we know phenomena, there's certain phenomena in the atmosphere where the large-scale circulation is there first, or mesoscale circulation even, like a land sea breeze. And then convection occurs where that land sea breeze is. And there are other occasions, especially over the ocean, when the SST gradients are weak, circulations might be relatively weak initially, and convection bubbles up, and then that induces a circulation, which then makes more convection in the region where we had only very little. So, to come back to your question, there's both a thermodynamic control on the convection, which is basically surface fluxes, you get the growth. If you think about the thermodynamic control, so shallow convection is entirely controlled by the surface fluxes. Why doesn't it go deep? It doesn't go deep because you have an inversion on top, right? And it can't get through. It's just simply, there's not enough energy to push the clouds through that inversion. Why is that inversion there? Oh, because we have an even larger scale circulation called the Hadley cell, which makes this very strong subsidence, which is very strongly related to the ascent in the deep convection in the ITCZ. So it's all connected, all right? So why does shallow convection then sometimes do go deep? Well, if you think about diurnal cycle over land, for instance, the intensity of the surface fluxes increases because the sun, the energy from the sun increases in the diurnal cycle, and eventually it's enough to make the clouds break through any inversions. The inversions are never as stable as a trade wind inversion because they're not part of a big system. If you have strong high pressure, you don't get convection, again, because you get a strong inversion. So in that sense, dynamics controls convection in that sense. And if you have a high pressure system, you can heat the surface as much as you like. You won't get deep convection if the high pressure system makes a strong inversion, right? So there's a dynamic control on it. And then there's the thermodynamic control. And it's the balance between those two, how they play off each other, against each other. They fight against each other, that in the end determine where convection will occur. And the other view that I actually also follow a lot, if you take a more weather-oriented view, there's always waves in systems, right? There's troughs, there's ridges, there's waves, there's little lows, all sorts of things. And I think most of the convection on Earth has to do with those. Not all of it, but most of it, even over the ocean. You find that there's little convergence lines because they're small. There's an argument by Rit Carbone a few years ago that even microgradients in the SST, so even just a half a degree or 1 degree gradient in SST, that is mesoscale because there are eddies in the ocean as well, is enough to make a convergence line. Convection forms on that convergence line. So I think there's a lot of dynamical systems that set where the convection will occur. So it's actually a very difficult question. What determines whether convection can occur or not? In the models, what you do is you test for whether you lift a parcel, how high will it go in the atmosphere. But you test it after you apply the changes due to the adiabatic motions, to the large-scale motion. So you already cool the atmosphere from adiabatic ascent, and then you test your parcel. So you have this dynamic control built in, essentially.
So this in this figure in the Amazon. So It's a frequency of organized convection is increasing, right? It's the light blue color. But
So rainfall is increasing.
but intensity of organized convection is decreasing, right? It is
Yes.
rediscale.
Yes.
And it is just opposite over India, right? Central Indian plain.
But
Right.
India has a very small
Frequency
signal.
of organized convection seems to be
So there's a small increase.
reducing a little bit, whereas intensity of organized convection is.
Yeah, I wouldn't look too much. So you see, only where you have these yellow stipples is the result significant.
Is it from trim or?
Yeah, well, we did two. This is from SKIP and GPCP, but you get
Not
the
from
same
trim.
from trim.
So that he has not checked, right?
This is not trim.
It's not trim. So can we, cross check from trim?
Yes. And we also, I didn't show this, you can also look at another definition. So this is the definition that uses the cloud signature to define what organized convection is.
Okay.
You can also check the same thing, and it's in the paper. Independent data set. You use trim and you say stratiform versus, so how much of the rain, of the total rain is stratiform?
Oh, he has done?
And we've done that, and we get the same result.
Oh. Any other questions to Christian?
So, what causes convection to organize in flows? Because there are some theories for meteorology which does not seem to fall.
So the question was, I repeated so people at the back can hear. The question was, what organizes convection, right? What is